Okay, in this video we're going to look at factoring what's called differences of squares here. Now, let's start off here with establishing that we know what perfect squares are. So a perfect square here is something that I can take the square root of and get a nice whole number. So you really should know your perfect squares up through 1 times 1 to 15 times 15. Okay, so 1 times 1 is 1, so 1 is a perfect square. And then 2 times 2 would be 4. Okay, I hope you catch on to the pattern here. 3 times 3 would be 9. So we have 1, 4, 9. If I kept going here, I would get 25, 36, 49, 64, 81, 100. Okay, so that's 5 times 5, 6 times 6, 7 times 7. So notice if I took the square roots of these values, they would give me a nice perfect square. So this would keep going here. And so the next one will be 121, and then 144, and 169, and 196, and 225. Okay, you may not know those at the end there, and it's probably a good idea to take a look at those and try to learn those. Now, in terms of variables, what we have for perfect squares, if I have a variable, what makes a variable a perfect square is simply if it just has an even exponent. So x squared is a perfect square. Okay, x to the 4th would be a perfect square. And even x to the 6th is a perfect square. And I could keep going there. So all I have to have is an even exponent. And the reason why I can say, well, the 6 is not a perfect square, but x to the 6th is because x cubed times x cubed would be x to the 6th. So the square root would be x cubed. So notice there's a pattern when we do the square root of something with a variable raised to a power. You're actually dividing it by 2, okay, unlike a whole number right there. Now, so I hope you know your perfect squares here. That's going to be crucial. Now, let's look at another term here before we actually get to factoring differences of squares here. Let's look at what we mean by conjugates. So the conjugate of an expression, it's just better here to show you. If I have, for instance, x plus 4, okay, the conjugate of x plus 4 would be x minus 4. So the conjugate is basically the same thing. It's a binomial factor, and all that changes is the middle sign right there. So let's do a couple more examples of that.
Please report to the gym. 11 brothers.
If I have x minus 7, then the conjugate of that would be x plus 7. Okay, so again, it's the same numbers. The only thing that's changing there is the middle sign. Okay, let's do one with a negative first here. So say I have like negative x plus 3. Okay, the conjugate would be negative x minus 3. So notice we don't change both signs. The only sign that changes is the signs here that are in the middle. Okay, so they're the same binomial factor. They're almost the same there, except for the middle sign. Let's do one more here. So what if I have, say, 2x minus 3? Okay, the conjugate would be 2x plus 3. And when we factor a difference of squares, this is what we're going to get. It's the product of two conjugates. Now, before we actually factor, I know I'm building up to factoring here, let's look at what happens when we take two conjugates and we multiply them together. So if we see this, we probably think here this would be the full method, and that's pretty much correct here. So we're going to do first, outside, inside, last, and we're just going to notice something that happens, though, that's sort of a special product when you multiply two conjugates together. So first would give me x squared, outside would be 3x, inside would be negative 3x, and then last, negative 3 times positive 3 is going to be negative 9. Now notice, when you multiply conjugates, these signs are always different. Therefore, this last number is always going to be negative. When I multiply a positive times a negative or a negative times a positive, it's always negative. Now, here's the real significance of multiplying conjugates. Look what happens in the middle. 3x minus 3x would just be 0, so it would basically go away. And all you would have left would be x squared minus 9. So what we say, and this is only applying to conjugates here, so instead of the full method, the outside and the inside products, they always cancel out. So I just call it the FLA method. Okay, it's just F and L, so it's just first and last. So if I notice that I'm multiplying two conjugates, I can just do the first and the last multiplication. So let's do that on this problem. Let's not do the whole full method because these are conjugates. See, one is plus, one is minus, but everything else is the same. So let's do first times last here. X times x would be x squared, and 7 times negative 7 would be negative 49. Okay, so what would happen in the middle is you would get a negative 7x and a positive 7x, and they would go away just like this right here. Okay, let's look at one more, and then we're actually going to start factoring by difference of squares. Now, so on this one, notice they are conjugates. This is plus, this is minus, but everything else is the same. So all we have to do is first and last, and keep in mind, you can only do this shortcut
Seniors, please report to the gym. Seniors.
when they are conjugates of each other. You'd have to fold this out otherwise. Now, so first and last here, this is going to give me 3x times 3x would be 9x squared, and then 2 times negative 2 is negative 4, so sure enough, it's always going to end up being minus when we put those together. Now, let's actually factor here a difference of squares. Okay. Now, one thing about when we factor a difference of squares, notice that when we label this, it's with the word difference. Okay, so a difference of squares has to be a binomial, so that means it can only be two terms. They both have to be perfect squares, and it has to be a difference. Okay, so this sign right here has to be minus. Okay, it cannot be plus. Now, factoring a difference of squares is probably the easiest factoring to do as long as you can recognize perfect squares. So when I saw these numbers, or when I made up this problem, I used perfect squares right there. So remember what's going to happen here with a difference of squares is it's going to be the product of the conjugates of the square roots of these numbers. Now that kind of sounds complicated, but it's really not. So they're going to be two conjugates, so there'll be one with plus, one with minus, and then the factors are just the square roots of these numbers right here. So the square root of 4x squared is 2x, and then the square root of 49 would be 7. So we have 2x minus 7 times 2x plus 7. So notice I just took the square roots to get the two factors, and they're conjugates of each other. So you do one with plus, one with minus. And the order that you write them in really doesn't matter right there. Okay, I usually change it up a little bit. Now, let's look at this one. Looks very, very similar right there. However, this is not a difference of squares. Okay, to be a difference of squares here, this has to be minus. Remember, multiplying conjugates, you always get a negative times a positive, and that's always going to give you a negative back. Well, that would not work right here. So this is actually what you would call a sum of squares instead of a difference of squares. A sum of squares cannot be factored, so that's what I'm going to write right here. Okay, on this one, I can't factor that. And the reason why here is because this is a sum. It's not a difference. It has to be minus. All right, let's look at these other ones now. Okay, on our next one here, 9x squared minus 100. Okay, let's notice it is a difference, and they are both nice perfect squares. So all I have to think about is what is the square root of this number, and what is the square root of this number. So the square root of 9x squared would be 3x, and then the square root of 100 would be 10. So I'm going to have a 3x and a 10, and a 3x and a 10. Now, they have to be conjugates, so all that means is one is plus, one is minus. Okay, doesn't really matter at the order that you do that. So it's really simple because the factors end up really turning out to be the same, except for one has an opposite sign. Now, this one, x squared plus 64, so we might say, okay, the square root of this is x, the square root of this is 8, but it's a sum. So recall here, we can't factor when it's a sum of squares. This has to be minus right here. Okay, let's look at the next. We got about 4 more here. Okay, 100x squared minus 1. All right, so this is a difference. Now 100x squared is a perfect square. It would be, the square root would be 10x, and 1 is a perfect square. The only thing, the square root of 1 is just 1. So I'm looking at the numbers 10x and 1. So all I have to do is say a 10x plus 1, and then do the opposite, a 10x minus 1. Remember, these are called conjugates of each other. So the difference of squares is the product of two conjugates. All right, x squared minus 64. This one's really easy. So now recall, we could not do x squared plus 64 because it was a sum. Now that this is a difference, I can factor this. So my square root of x squared there is x. The square root of 64 is 8. So we just do 1 with plus, 1 with minus. X plus 8 times x minus 8. Let's look at this one. X squared minus 81. So notice those are nice perfect squares right there. So we can just think the square root of x squared is x, and the square root of 81 is 9. So this would be x plus 9 times x minus 9. Okay, and last one here, and notice this one is kind of backwards. Normally we like to see it in standard form where this comes first, but you don't have to really have that when you do a difference of squares. All that matters is this is a perfect square, this one's a perfect square, and it's minus. So the square root here is 5, and then the square root of this number would just be x. So I'll get 5 minus x times 5 plus x. And of course, we can write that backwards there. We could write 5 plus x times 5 minus x if we want to. The order of the two factors doesn't matter there.